Hello, this is the problem solving video for lecture 1. So first problem, the question is, what is the surface atomic density of a silicon crystal at the 001 plane at room temperature? Here, we discuss the solution, but before we proceed, we highlight first the important details in the question. So we are being asked about the surface atomic density of a silicon crystal. That's why we are given this specific plane, the 001 plane, and we are also given this figure to help us identify what is being referred to as the 001 plane. And so next, we are also given that it is for a silicon crystal which follows a diamond lattice structure. So if we follow, or if we draw a diamond lattice unit cell, we'll have this one, and highlighting the 001 plane, so we highlight the top portion. Now, to imagine the surface atomic density, we are actually being asked how many atoms are there in the surface per unit area. So here it wouldn't matter how much of the atoms are inside the unit cell, since the unit cell is a 3D structure, but we are being asked about a surface atomic density, so that is in 2D. So if we try to expand and repeat the unit cells in a crystal, so we'll have this pattern here, but highlighting only what is covered by one unit cell, then we'll have this highlighted figure. So since the unit cell is cubic, then each side must be of length A, or the lattice constant. And since we are given from the question that we are talking about silicon at room temperature, we know that the lattice constant for a silicon at room temperature is 5.43 angstroms. So we can now proceed with the computation. The surface atomic density is just the number of atoms per unit area. So if we consider this highlighted area, we have 1/4 of the atom inside the area for each corner, and we have 4 corners. So 1/4 times 4 plus 1, which is completely inside the square area. And the area of the square is a squared. So therefore, we simply have 2 over 5.43 times 10 to the minus 8 centimeters. Since an angstrom is 10 to the minus 10 meters, if we convert that to centimeters, we multiply by 100, or 10 to the 2, so we end up with a multiplier of 10 to the minus 8. Now, with the help of our friendly calculators, you should be able to compute the following. So the surface atomic density for a silicon crystal at the 001 plane at room temperature is 6.783 times 10 to the minus 14 atoms per cm squared. And that's the final answer for problem 1. Okay, we proceed to problem 2. So for problem 2, we are tasked to determine the hole concentration for a pure silicon crystal at room temperature, or 300 K. So for the solution, note first that we are given this pure silicon at room temperature. So a pure semiconductor, the free electrons and holes are created in pairs, and their value is given by some Ni. So actually we have N is equal to P is equal to Ni. However, we are being asked for the hole concentration. So we just type in here P is equal to Ni. Now specifically, For silicon at room temperature, we have noted in the lecture, we have shown in the plot and highlighted that for silicon at room temperature, the intrinsic carrier concentration Ni is equal to 10 to the 10 per cubic centimeter. So since P is equal to Ni and Ni is 10 to the 10, therefore P must also be simply 10 to the 10, and we've actually already answered the question. So we just note here that this is actually just the same with free electrons. So for a pure silicon crystal at room temperature, the whole concentration is 10 to the 10. This value may differ if we are talking about a different semiconductor, or if we are talking about a different temperature, or if the silicon is not pure. The last problem we'll discuss in this video is problem 3. So for problem 3, we are given that pure germanium crystal at room temperature has 2,000 times more holes per unit volume compared to pure silicon crystal at room temperature. So the question is, how many free electrons per cubic centimeter does pure germanium have at room temperature given this information? For the solution, we note first that all variables mentioned are for room temperature. So in the given, it is said that pure germanium crystal at room temperature has 2,000 times more holes per unit volume compared to pure silicon crystal, again, at room temperature. So how many free electrons does per cubic centimeter does pure germanium again have at room temperature? So that's important since what we know for silicon crystal at room temperature is that Ni is equal to 10 to the 10. Next, since we are given a pure germanium, and we are being asked about this pure germanium. So for a pure germanium, we also have N is equal to P is equal to Ni, but we'll just add this subscript to denote for germanium. For pure silicon as well, we have N is equal to P is equal to Ni. Sorry, this should have a parenthesis. And we use this fact right here that Ni is equal to 10 to the 10. So let me just remove some of the highlights. Now from the given, it is said that a pure germanium crystal has 2,000 times more holes per unit volume. So this quantity right here is the holes for germanium, and it is compared to the holes per unit volume of a pure silicon crystal at room temperature. So this orange one here is this one. And finally, we are being asked how many free electrons we have for pure germanium. And that variable is here, N of germanium. So since we have this blue, the N of germanium of a pure germanium just equal to this green one, the holes of a pure germanium, then we'll just need to compute the density of holes for pure germanium. And from the given, its value is 2,000 times more than that for silicon. So P of germanium is just 2,000 times 2,000 times of that for silicon. So 2,000 times Ni of silicon, which is just 10 to the 10. So 2,000 times 10 to the 10 will simply give us 2 times 10 to the 13. And since P for germanium is 2 times 10 to the 13, then N would just be simply equal also to 2 times 10 to the 13. Although there is just a minor problem with the highlight. So the actual problem is asking, we are being actually asked for the electron concentration for germanium at room temperature. So the final answer is N for germanium is equal to 2 times 10 to the 13 per cubic centimeter. And that's the final answer. So we've actually answered already the 3 problems, and that's the end for the problem solving video for lecture 1. Thank you very much.